All right, so I wanted to do some solutions for these last problems and of course review part 2. Start with problem number 1. And if you look at that, we have a mass on a tabletop connected with a string over a pulley to another mass. And so if you look back at it, the stuff that we've had before, if you remember, we had coupled motion. That was unit 4, where we looked at objects, or unit 3 and unit 4. I don't remember which one where we started it, but it could have been unit 3 and then we went on to unit 4. But to do that, looking at the problem, we'll need to do a free body diagram. But then it asks a little bit about a pulley, if we include the pulley having mass, what that's going to entail. So when I look at 1A, what it says is, before you do any calculations, it says if mass A was really big compared to mass B. So the mass on the table is really big and the mass that's hanging is very small. In the extreme case, if A is kind of infinitely big compared to B being almost 0, A is not going to move. So there's going to be 0 acceleration. And then if we flip that, if we have a really heavy mass hanging, it's not going to be dragged back very much, so it's going to be close to the acceleration due to gravity. That's what I think is going to happen. And we'll have to check that later with our equations. But B says to draw a free body diagram, so draw a dot for each, so I labeled it A and B. Both of them have weight. In this case, I just drew the arrow for B to be slightly bigger than A, just to show that they're not equal. But A is balanced on the table by a normal force. But then they are connected by a string, so they both have a tension, and tensions pull. So we have a free body diagram that looks like that. So the two tensions are equal in this case. Then if we want to solve for the acceleration, there's a couple ways we can do it. Basically what you do is the coupled motion version that we did before was you figure out net force equals mass times acceleration. We look at the outside forces and all of the mass. So the only outside force that isn't canceled out is the weight of B, because the weight of A and the normal force cancel each other out, and the two tensions cancel each other out. So, because it's all connected. And so you have the net outside force being the weight of B, and then you have the combined mass, because they have to move together with the same acceleration. And then you solve for that and get that the acceleration is the weight of B divided by the combined masses. Remember, we got that a number of different times. Another way you can do it, if you don't remember coupled motion, is just realize that they have the same acceleration, but set that up and look at mass A and figure out it's only the tension that makes it accelerate. Same thing for B, but it's the tension, it's the difference in the tension and the weight that makes it accelerate. You realize that B is going to accelerate in the negative direction, and you combine those two equations and you get the same result. Just solve for acceleration. You can plug in the tension into the equation for B from equation for A, and then solve for the acceleration. So you're able to get that to work. All right, so we've gotten that result before. Now in D, we look at what happens if A is really big or if B is really big. So if B is really big, then it goes away and you only get the acceleration due to gravity. So if A is 0, you only have mass B cancels and you get the acceleration due to gravity. But if mass B equals 0, then because it's in the top and the bottom, you plug that in and you get 0. So that matches my prediction in the previous thing there, in part A. But then for the case where it has mass, because they have unequal amounts, there has to be an unequal tension, because otherwise you're not going to accelerate the pulley, because if the pulley has mass, it requires force to accelerate it. The net force and the net torque are not 0. So the only way to get it to accelerate in the correct way is if T2 is greater than T1.